So what we have seen so far is that we have applied the valence bond theory, right, to a variety of compounds that pretty much range in molecular geometries from octahedral to tetrahedral to square planar, and we've observed that the hybridization is still consistent with what this valence bond theory is actually telling us. However, what the valence bond theory does not tell us is why certain ligands are associated with the formation of a high spin complex and the formation of a low spin complex. What actually drives this forward, what dictates the formation of one versus the other. So we pretty much need to introduce a new theory. We can't rely on the valence bond theory anymore. The theory that we're going to be using here is actually called the crystal field theory. And the crystal field theory is pretty much an electrostatic model, which means that we're going to rely on the fact that the diatomic orbitals in a metal complex are not happening at the same energy level. They are not actually degenerate, right? They are not at the same energy level. So remember, so far we have said that those diatomic orbitals, they are exactly at the same energy level. Well, we know that this is not true. They should be split into two different energy levels. We're also going to assume that the ligand electrons, they create an electric field around the metal center. So if you think about having a metal center that is actually a cation, the ligand electrons around that cations are actually going to create an electric field. So we're going to have electrostatic attractions between the positive charge on the metal cation and the electrons coming from the ligands, right? So plus in the center, negative around it, they are going to be attracting each other. Obviously, because of these electrostatic attractions, there are no metal-ligand covalent interactions, right? So if we start applying this theory to the octahedral crystal field theory, so applying this theory to octahedral complexes, we again are assuming that there's an electrostatic interaction between the metal ion and the ligand, and we also are assuming obviously that because all of these ligands are providing electrons, they are repulsing each other, right? Minuses and minuses among the ligands are repulsing each other, whereas the metal cation and the electrons from the ligands are attracting each other. So if we would assume that the electrostatic field, that crystal field, were actually spherical, that means that the energies of all of the 5 diatomic orbitals will be actually raised by the same amount upon coordination with the metal cation. However, we know that this is not the case because the dx squared minus y squared and the dz squared atomic orbitals, they point directly at the ligands, while the other 3, the dxy, the dxz, and the dyz, they point between them. So the energy of these two different sets of atomic orbitals is not at the same level, right? If we actually look here, so if we are actually looking at how the two sets of diatomic orbitals are split in terms of energy, we know that if they would be degenerate, they would be at the same energy level. We are having an electrostatic field that is created, right, by the fact that we have those ligands around the metal cation. So the energy of the different atomic orbitals here is raised, and they are furthermore split into two different levels because we have some of these diatomic orbitals that are pointing directly at the ligands while the others are pointing between the ligands, right? So the ones that are actually pointing directly at the ligands are actually raised, right? That's why the dz squared, dx squared minus y squared are higher in energy, whereas the dxy, dxz, and dyz are lower in energy. Okay, so this set actually is called the T2G set, and this upper set here is called the EG set, right? So if we represent this on a piece of paper, when I'm going to ask you to actually represent the splitting of the diatomic orbitals, what I am referring to here is this. So obviously here, right, is the energy level, and then you're going to have the 3 diatomic orbitals here, which are the dxy, dxz, and dyz, and really it does not matter those don't have to be in this particular order. You can have the dxz here, the dxy there, and the yz at the end. It really doesn't matter as long as those three here are in the lower set of energy. And this lower set of energy here is labeled T2G, and T means that it stands for triply degenerate level. So T is the first letter of triply, and then the other two, which are raised in energy, right, with respect to the spherical field. These are the dx squared minus y squared and the dz squared, and it does not matter which one goes first, and that's the EG set. So E here, unfortunately, stands for, not for doubly, I mean, it actually stands for doubly degenerate, but it's not a D, it's an E. And the little G, the little subscript G, actually stands for the German word gerade, which means even. So they are even in terms of they are both, all of them, right? Those three are at the same energy level, and the two of them here are at the same energy level. So the T2G set, right, is actually lower in energy, right? So it's a lot more stabilized versus the EG set that is higher in energy. So those atomic orbitals are actually destabilized, okay? And they are not destabilized actually with respect to the origin. So it's not, if we actually are looking at the way these two sets are spread out, right? There's actually a difference in the spreading of those two sets of atomic orbitals. So if we would actually look at, the way the T2G set, right, and how it is far apart from the EG set, if we are thinking that this is the origin here, the EG set is a lot more destabilized than the T2G set is stabilized, right? So if we are looking here at the difference between the origin and the T2G set, right, the difference is a lot smaller than the difference between the origin and the EG set. One way or another, the difference here between those two sets, the difference in energy, is actually called the crystal field stabilization energy, or CFSE. And so that stabilization energy, right, is usually labeled delta because it's a difference in energy between the two sets. And that delta is here having a little subscript oct for octahedral. We'll see that it changes a little bit when we are applying this crystal field theory to tetrahedral complexes. Okay, so what is really important is that this delta oct here is actually not the same for all of the ligands and all of the DN configuration that we are going to be looking at. Depending on the DN configuration and depending on the type of ligands that we have, that delta oct is also going to change in magnitude. It's either going to be obviously smaller or much larger. So how do we know how this delta oct actually changes? Well, it has to do with the fact that we have different types of ligands. Remember, the types of ligands are actually going to be giving rise to either a high spin complex or a low spin complex. But how do we know, and how can we determine which ligands give rise to what type of complex? So we need to introduce here the fact that these ligands can be ordered, and the way they are ordered is along a spectrochemical series. That spectrochemical series that is represented here shows you that when we move from the left to the right, the delta oct actually increases, right? So these ligands are actually arranged in order of increasing delta oct, right? So the ligands further to the right, right, have the larger delta oct. The ligands obviously further to the left have the lower delta oct. This means that those ligands that are here are weak field ligands. They are weak, right? Their delta oct is very, very small. So they are weak field ligand. The ligands to the right are actually strong field ligand, which means that they have a much larger delta oct. So looking at the spectrochemical series, right, we have we can identify some of the ligands that are weak field ligands and the others that are strong field ligands. And where we actually switch from weak field ligands to strong field ligands is right here after water. So up to from iodide all the way to water, we have weak field ligands. Starting at thiocyanate all the way to carbon monoxide or the carbonyl ligands, we have strong field ligands. You may notice here that the thiocyanate ligand that we talked about before, remember we said that this is an ambidentate ligand because we can either have the sulfur coordinating to the metal center or we can also have the nitrogen. Well, that's exactly what is important here to remember, is that when we actually have the coordination through the sulfur, it's a weak field ligand. If we have the coordinations through the nitrogen, it's actually a strong field ligand. So it's really important to look carefully where actually to which element the metal center is coordinated. Is it to the sulfur or is it to the nitrogen? Okay, so the spectrochemical series is something that you're going to have to know. So you're going to have to, I'm not going to give it to you. You're going to have to know, for example, that, you know, fluoride is a weak field ligand. You're going to have to know that ammonia is a strong field ligand. So that you're going to have to know. The spectrochemical series here is important for you to actually remember. But we're going to apply those ligands. We're actually going to apply this crystal field theory with many of the ligands that are listed here. So the more you're going to use them, you won't even have to remember if they are a weak field or a strong field ligand. The other important point here is not just, you know, the spectrochemical series and how those ligands are arranged with respect to the delta oct, but most importantly, that when we have a strong field ligand, what does that mean we have a strong field ligand? That means that it's going to actually favor the formation of low spin complexes. And so low spin complexes, so strong field ligands, right, are favoring the formation of low spin complexes, which means that, so if there's strong field, that means that there's actually a large delta oct, right? So the two sets of diatomic orbitals are actually really far apart in energy, right? So for example, if we look at a strong field ligand, right, such as cyanide, that's a strong field ligand, right? Then we are having here a large delta oct, right? Because there's a large difference in energy between the T2G and the EG set, those electrons here don't have enough energy to also be occupying the higher energy set, EG. So because it's too much of a gap here, this is too much, right? The gap is, it's just like, you know, in an insulator, right? The gap is too large, therefore the electrons don't have enough energy to jump from the lower set to the higher set. It's exactly the same thing here. So this ligand here, the DN configuration for ion is D5. All of the 5 electrons are actually going to stay in the lower set of energy. That's why when this is happening, whenever we have a strong field ligand, we are having the presence of a low spin complex because the electrons are occupying the lower set of energy. On the other hand, what we're having, you know, pretty much with a weak field ligand is the opposite. If it's weak field, that means that the delta oct, right, is much smaller. So the electrons do have actually, or will have enough energy upon coordination to actually be spread out over the T2G and the EG set. So here you see those 5 electrons that are actually spreading out pretty homogeneously versus those 5 here, which are giving rise to an uneven distribution of electrons, right? So here we have water, H2O. H2O is a weak field ligand. It's going to give rise to a high spin complex where the 5 electrons from the ion 3+ are actually going to be spread out over the 2 sets, okay? So one of the things that I actually really wanted to kind of look at, and something that we haven't looked at before, is the fact that some of these ligands that are mentioned here, for example, this one, that's the oxalate ligand. You guys know that this is the thiocyanate. En stands for ethylene diamine, BPY stands for bipyridine, and PHEN, phen, stands for phenanthrene. You guys have no idea how those ligands actually look like. How do they look like? What is their composition? So I just want to briefly draw them for you. The oxalate ligand here. The oxalate ligand. There's a lot of oxygen in this ligand. And so what's happening here, right, if you are looking at, the way this ligand looks like, right, you see there's 2 oxygen here, 2 oxygen here. This is actually a bidentate ligand where the metal center can actually be coordinated in 2 points, right? So there's 2 points of attachment to the metal center. We are calling this type of ligand bidentate ligands. As a matter of fact, all of the ligands that are listed here are bidentate, right? So they pretty much bite the metal center in 2 points. Ethylene diamine, you may remember, this is an amine. There's 2 of them. Ethylene diamine, again, the metal center here can actually coordinate to the 2 nitrogen from the amine groups. Again, this is a bidentate ligand. Bipyridine, so if we are actually looking at bipyridine, so it's you may remember pyridine, and if you don't, it's perfectly fine. This is pretty much pyridine right here, but it's bipyridine, so there are just 2 of them. It's a symmetrical ligand. And again, this is a bidentate ligand. The metal center can actually coordinate to both of the nitrogens here in the bipyridine ligand. And finally, phenanthrene. It's a little bit more of a bulkier molecule here. Again, it's a bidentate ligand. Okay, so oxalate, bidentate, ethylene diamine is a bidentate ligand, bipyridine is a bidentate ligand, and phenanthrene is a bidentate ligand. Okay, as you notice here, the oxalate is actually the only one of the 4 that we have just drawn that is actually a weak field ligand. The other 3 are strong field ligands. Okay, so we already talked about the fact that why are weak field ligands associated with the formation of high spin complexes and vice versa. We actually talked about that. We also talked about the fact that, when we have when we go from weak field ligand to strong field ligand, right, here the delta oct is small, here the delta oct is much larger, right? Because the delta oct here is small, there's going to be enough energy for the electrons to actually be spread out over the lower and the higher set of energies, so we're going to give rise to a high spin complex. And vice versa, if we have a strong field ligand, the difference in energy between the T2G and the EG set is much larger, so the electrons are actually going to stay in the lower set, and we're going to have the formation of a low spin complex. Okay, all right, so we could actually look at different DN configuration. I think it's pretty clear that when we are looking at a D1, obviously you're only going to have, if we again represent the 2 sets, if we look at a D1, we can only have 1 electron, and that only can be in the T2G set. If we have a D2 system, right, we're obviously going to have 2 electrons and they're going to be spread out over the first 2D. Same thing for a D3, the third electron will actually be in the third d atomic orbital. It's when we start looking at a D4 system, right, that there are 2 possible ground state configurations there. The reason for that is because you can imagine, right, that we can have 2 options here. The reason why we can have 2 options
It's fine. Just take your time.
is because we have a technical issue here. All right, when we are looking at D4, either my 4 electrons can all be in the lower set, so the T2G set, which means that in this case we are having a low spin complex. But depending on the ligand, right, if we actually have a ligand, right, that is weak field, we're going to have a strong field, a high spin complex. And so in a high spin complex, my 4th here electron is actually going to be in the EG set. In this case, we're going to have a high spin complex, right? So low spin complex, that means the ligand here must have been strong field. High spin complex, the ligand here must have been weak field, okay? Here in a low spin complex, right, we have a large delta oct. In a high spin complex, we have a small delta oct, okay? So if you think about it, for D1, D2, and D3, we really don't have actually the choice. D1, D2, and D3 will always be low spin independently of the nature of the ligand. But it's when we start having D4, D5, and even D6 that we could have either low spin or high spin depending on the nature of the ligands. But if we have D7 all the way to D10, we don't have a choice here. It's always going to be high spin, right? The reason for that is because you can only put 6 electrons in the lower set, right? So after D6, if you switch to D7, you don't have a choice. You actually have to put your 7th electron in the upper, obviously, EG set of energy, okay? So what I would like you to do, and we obviously, start talking about this, and the answer is already on the slide that I showed you earlier. If we go briefly here through this practice problem, and I want you to be able to do this just so that you have the answers written down and you practice. We look at the oxidation state, the DN configuration, and the shape here based on the Kepler model. Then we can look at the presence of the lower high spin complex and draw the splitting of the d atomic orbitals, right? So just to go back to what we talked about on the slide, right? Those 2 complexes here, one has 6 water ligands, the other one has actually 6 cyanide. We know that here iron should be iron 3+. Iron has 8 valence electrons, so the DN configuration is 8 minus 3, that's D5. Look at the shape based on the Kepler model. We have 6 ligands, it has to be octahedral, right? Water is a weak field ligand, therefore it's going to give rise to a high spin complex. And the way that we're going to be drawing the splitting of the d atomic orbitals in a high spin complex, this is T2G, this is EG, right? My 5 electrons are going to be spread out evenly over the T2G and the EG set. The delta oct here in this case is small, that's why we can have an even distribution of electron density. On the other hand, we have here a complex that has 6 cyanide. That doesn't change the oxidation state, and it doesn't change the DN configuration either. We still have Fe3+, D5, 6 ligands, it's still octahedral, right? However, what does change is the fact that cyanide is a strong field ligand. So we're going to have the formation of a low spin complex. Therefore, now my 5 electrons, right, are all going to be in the T2G set. So we're going to have the electron density that is now going to be concentrated in the lower set, which means that it's completely uneven and it's also a lot more unstable because of that. Okay, so as a summary here at the bottom of the page, I kind of summarized what I've told orally, which means that D1, D2, and D3 are always going to be low spin independently of the ligands. D4, D5, and D6, well, they can either be low or high spin depending on the field of the ligands. If they are weak field, they're going to be giving rise to a high spin complex. If they are strong field, they're going to give rise to a low spin complex. And then for D7 all the way to D10, we don't have a choice. They are always going to be giving rise to the formation of high spin complexes because we can only put 6 electrons in the lower D set. And so that's pretty much a summary of some of the questions that I will probably ask you on the next test in terms of looking at oxidation state, DN configuration, determining the shape based on the Keppel model, and justifying if we actually have a low spin or high spin complex, and then drawing the splitting of the diatomic orbitals with the two T2G and EG set, and then putting the electrons where they belong. Okay, so the next time when we're going to meet, we actually are going to start looking at the fact that those complexes, especially octahedral complexes, right, they not always look perfect. They can be actually some distortions. And then we'll move forward to tetrahedral and square planar crystal fields, how the crystal field theory can be applied to both of those molecular geometries. All right, I'll see you next time.